All right, this is part 5 of our notes from the graphical representation of VLE. In this section of notes, we'll talk about azeotropic systems. So far, we've looked at TXY and PXY phase diagrams of systems involving ideal mixtures, right? So mixtures of alkanes, mixtures of compounds that are chemically similar. So in this set of notes, we'll briefly look at a couple of examples of azeotropic systems, an azeotropic system being a system in which the two compounds are not chemically similar, and we observe pretty substantial deviations from ideality. We'll talk more about azeotropes and the theory behind azeotropes much later in the text, but here we're going to introduce them in the concept or in the context of TXY and PXY phase diagrams. Okay, so let me close that. All right, so here's the example TXY and PXY phase diagrams we've looked at, heptane and decane. Okay, and so here on the left I have plotted a TXY, and on the right I have plotted a PXY. Okay, so the TXY phase diagram, pressure is constant, and a PXY, temperature is constant. Okay. So a couple of notes before we look at some example azeotropic systems is if I look at my TXY phase diagram, if I have a mixture of composition Z, okay, it's some composition between the pure component limits. So if I'm in the liquid region and I heat it up into the two-phase region, right, the point at which my first bubble forms is my bubble point, right, is where I hit the bubble line. So the bubble point temperature would be where at this composition I hit my bubble line. So this would be the temperature at which my first bubble forms. And then if I continue to heat it up, it's going to continue boiling all the way until I hit my dew line, which is the point at which essentially my last liquid drop vaporizes. Okay? And so for this idealized system, or for a normal system, for a mixture, it's going to boil over a range of temperatures. Okay? Now compare that to the two pure component limits. If I have pure component 1 and I heat it up, okay, when I reach my bubble line, right, at this pure component limit, my bubble line and my dew line, are one and the same. And so what happens then is I directly transition from a liquid to a vapor, right? So pure component 1, if I heat it up to its pure component boiling point, that's the point at which it's going to directly transition from a liquid to a vapor, right? Same goes for pure component 2. Okay. The other thing I'll point out is, again, if I take this liquid mixture and I heat it up, okay, when I plot things with respect to the most volatile component, okay, when I enter the two-phase region, I'll get phase splitting along this isotherm. Remember, pressure is already fixed throughout my system. I read off my vapor composition from the dew line, liquid composition from the bubble line. Okay, and so we plot things with respect to the most volatile component because my goal is to concentrate the most volatile component in the vapor phase, right, coming out the top of my column in the distillate stream. Okay, and so for this system, what we'll end up with is a Y that's greater than Z that's greater than X. So the concentration of my most volatile component in the vapor phase will be greater than the composition of the mixture I started with, and will be greater than the composition of my liquid phase. Okay, and we can kind of get the same information from a PXY, whereas we pointed out, my bubble line in a PXY for an ideal system is going to be characteristically linear, right? And deviations from this linear behavior will correspond to deviations from ideality. But again, that's something we'll talk much more about later on. All right, so the first example we're going to look at is an example of a minimum boiling azeotrope. Okay? And so what we have here is we have a binary mixture of methanol and carbon tetrachloride. Okay? And so if I think about carbon tetrachloride, well, it's a carbon with 4 chlorines attached to it, so I suppose it could participate in halogen bonding, but really has no sort of specific intermolecular interactions going on in that pure mixture. I compare that with methanol. Methanol's an associating fluid, right? So methanol can both donate and accept hydrogen bonds. Okay. So now when I look at my resulting TXY, all right, it's going to look very different from that idealized phase diagram we had on the last slide. Okay, and so what you'll notice is this is a TXY. Okay, so this bottom curve here is still going to correspond to my bubble line, right? My bubble line being what separates my liquid from my two-phase. This top line is still going to be my dew line, the line separating two-phase from vapor. Okay, but how we identify an azeotropic system is there exists a point where my bubble line and dew line touch. Okay, so when they touch just once, like in this example, we call that a monoazeotropic system, right? We have a single azeotrope over the composition region, okay, or over the composition range. And the azeotrope is identified, again, where my dew line and bubble line pinch. Okay. All right, so now in terms of trying to make sense of this, okay, it's a TXY, liquid's still going to be on the bottom, vapor up top, and underneath my dome I have two-phase. This would correspond to the pure component saturation temperature of component 1. This would correspond to the pure component saturation temperature of component 2. Okay, where we said, what's unique in the pure component limit is if I have a liquid mixture and I heat it up, all right, for a pure component, I'm going to transition directly from a liquid to a vapor, all right, in both pure component limits. What's unique about my azeotrope, or a system that exhibits an azeotrope, is if I have a system, right, that's at, say, this liquid composition, right, which corresponds to the same composition as my azeotrope, or the composition where my dew line and bubble line pinch. Right? If I were to take this mixture and I were to heat it up, all right, at my azeotropic temperature, my bubble line and dew line pinch, right, and what happens is for this azeotropic mixture, I also transition directly from a liquid to a vapor. Okay, so much like the pure component limits, if I have a mixture that's at my azeotropic composition, when I heat it up, I'm going to transition directly from a liquid to a vapor. Okay, and now when I think about what we've been doing so far with systems with these vapor-liquid separation processes, is the general idea is you heat it up into the two-phase region, you're going to get phase splitting in which you get a vapor phase, which is more rich with respect to the most volatile component. So then here, right, and so there you're concentrating the most volatile component off the vapor phase. Here, if you're directly transitioning from a liquid to a vapor, there's no possible separation for that mixture, right? So if I have a mixture of that azeotropic composition, there's no separation possible. Okay. The other thing we'll take note of is when we looked at our idealized system, our bubble point had some significance, right? The significance of my bubble point was if I started with the liquid mixture and I heated it up to my bubble line, right? So if I were to draw my isotherm at that bubble point temperature, that's going to give me the largest possible vapor phase mole fraction I could achieve in that separation, right? That's going to be the furthest to the right I could get on my phase diagram. Okay. So if I look here, okay, if I have a mixture that's to the left of my azeotrope and I heat it up, okay, I'm going to get phase splitting along an isotherm. Okay. So when I read across my isotherm, right, where I'm going to hit my dew line is going to be at my azeotrope, where my dew line and bubble line pinch. Okay. And so what we find is based on that bubble point calculation, where we found maximum Y's for on our TXYs before. If we do the same analysis here, we find that Y max is the same as the azeotropic composition. Okay. What else is unique is if I start to the left of my azeotrope and I heat my system up to the two-phase region and I get phase splitting along an isotherm, right? I'll get our standard behavior in this case that my vapor phase, Y1 is going to be greater than Z1, will be greater than X1. Right? This will be greater than the composition of the feed I started with, and they'll be greater than the composition of component 1 in the liquid. Okay. If I were to move over to the opposite side of my azeotrope, okay, I heat it up into my two-phase region, I get phase splitting along an isotherm, okay, but now things are going to flip. Okay, this is my bubble line, which is wrapping around. So when I heat into the two-phase region, my bubble line is now to the right. Okay, and so what happens is I get an X1 that's greater than my Z1, which is greater than Y1. So it's as if the role of the most volatile component and least volatile component have essentially flipped. Now I'm going to concentrate component 1 in my liquid phase, right, and not in the vapor. Okay, cool. Okay, and I will add, when we talk about a species being the most volatile species, how we identify that is using our pure component saturation temperatures. Right? So the component with the smaller pure component saturation temperature at the same P, we label as our most volatile component. Okay, and so here, our most volatile component is essentially behaving as if it were the least volatile component. Okay. All right, two more points that I'd like to make is one, when I first put the slide up, I said, here's an example of a minimum boiling azeotrope. Okay, what do we mean by that? Okay, so once again, if I talk about volatility, if I look at my two pure component limits, okay, this is going to correspond to my saturation temperature of pure component 1. So to given pressure, that's the temperature at which that pure component system boils. Okay, same thing over here if I look at the pure component 2 limit. Our most volatile species is going to be the one with the lowest pure component saturation temperature, the one with the lowest boiling point. Right? It's going to correspond to the system that's easiest to boil. Okay? And when we compare our two pure component limits, right, just like I said, the more volatile species is going to be the one that's more easy to boil. It's going to be the one with the lower saturation temperature. Now, if I look at my azeotrope, we said our azeotrope is unique in that if I have a mixture at my azeotropic composition, it's going to directly transition from a liquid to a vapor. Right? Here my dew line and bubble line pinch, so I'll directly transition from a liquid to a vapor phase. Okay. Now, why do we call this a minimum boiling azeotrope? If I look at the temperature for this, liquid to vapor transition for my azeotrope, or for an azeotropic mixture, it's less than either pure component. Okay. And so what this means then is if I have a mixture at my azeotropic composition, it's actually easier to boil that mixture than it is either pure component. Okay, so we call it a minimum boiling azeotrope. A minimum being it's easier to boil, or the boiling point of my azeotrope is less than either pure component limit. Okay. Now the last thing to think about is if we think about this as being, the ability, how easy it is to boil my system. Okay. So what we're suggesting is it's easier to boil my mixture if I'm at this azeotropic temperature or azeotropic mixture composition than it is either pure component. Okay, why do you think that is? Right. So minimum boiling azeotropes are caused by, essentially you could think of them as unfavorable interactions in solution. Okay, methanol and carbon tetrachloride don't really like each other, and as a result, it's more easy to boil that resulting mixture than it is either pure component, right? It's easier to boil the mixture than either pure component, that easier to boil, indicating we have some unfavorable cross interactions, right? And it's not always necessarily that the two components don't like each other, right? In this particular case, it's more so that methanol really likes itself, right? It would much rather interact with itself than with carbon tetrachloride, right? So minimum boiling azeotropes are caused by unfavorable interactions. And the last thing I'd like to point out is if I look at my bubble line for this system with a minimum boiling azeotrope, if I look at this region, I'll notice that my bubble line is flat. Okay, what this flat region of my bubble line indicates is that this is going to be a system that's partially miscible in the liquid region. Okay, so a flat region of my bubble line would suggest that we've already said this is a monoazeotropic system. We would further say that this is a heterogeneous azeotropic system. It's heterogeneous in that this liquid phase below my bubble line, right, in between these 2 points where I begin to curve, my system is going to be partially miscible. Okay, and so we'll talk about liquid-liquid equilibrium later on within this chapter. But if I notice a flat region, that suggests that these two pure components in the liquid phase are partially miscible, and so this is actually a heterogeneous azeotropic system. Okay, not all minimum boiling azeotropes are heterogeneous, but if I have partially miscible liquids, right, you can bet that they exhibit a minimum boiling azeotrope. Okay, cool. On the right-hand side, we have the same exact system just plotted as a PXY, and you get the same information. Things just flip, just like when we went from a TXY to PXY. And at PXY, we define volatility in terms of pure component saturation pressure at a given temperature. And when I think about pressure, okay, when I think about saturation pressure, the higher the pressure, the greater the affinity of that component for the vapor phase, right? Because what's pressure? It's just molecules exhibiting some force on their surroundings, right? And so what I can think of here is at a given temperature, my more volatile components could be the one with the larger Psat at a given T. So if my more volatile component, its Psat's greater than piece out of component 2. And we find that at the azeotropic composition, the vapor pressure of that mixture is going to be greater than either pure component. Right? But the same information can be pulled from a PXY, and here's how I would identify a minimum boiling azeotrope on a PXY, where that azeotropic mixture is going to have a vapor pressure greater than either pure component. Right? It's going to be more volatile. All right. So to wrap things up, right, we looked at minimum boiling azeotropes. Next is a maximum boiling azeotrope. We said minimum boiling azeotrope you could think of as resulting from unfavorable cross interactions. A maximum boiling azeotrope is going to result from favorable intermolecular interactions. Classic poster child of maximum boiling azeotropes is acetone chloroform. Right? So acetone is unique, so it has a carbonyl group, so it's a hydrogen bond acceptor, but it can't donate hydrogen bonds. So if you have a mixture of just acetone, it can associate with itself. If I look at chloroform, so it's CHCl3, so it has a hydrogen attached to that carbon, so that's a proton donor, and then I have my 3 chlorines, which can in theory participate in halogen bonds. But if I look at just pure chloroform, there's no specific interactions. But if I take acetone and I mix it with chloroform, they actually very much like to interact with each other. They'll associate with each other, where I'll get the hydrogen in chloroform donating a proton to the oxygen in acetone. So essentially, I get hydrogen bonding between acetone and chloroform. And like I said, this is kind of the poster child of maximum boiling azeotropes. And I've actually seen work from Oak Ridge National Lab where they've used neutron scattering to confirm this underlying behavior. Okay? And so in a maximum boiling azeotrope, I have strong or favorable cross interactions. And what happens is we're going to find it's harder to boil my mixture than it is either pure component. Right? Those molecules really, really like each other, so it's going to be much harder to vaporize them. So if I were to look at a TXY, okay, so here's a pure component saturation temperature of component 2, component 1. Right, so it's plotted with respect to my most volatile component. Right, component 1 has a lower pure component saturation temperature. Just as before, this is my bubble line, this is my dew line. Okay, at my azeotrope, we find that my bubble line and dew line pinch or touch each other. And so at the azeotrope, if I were to take a liquid, heat up to my azeotropic temperature, at that composition, I'm going to transition directly from a liquid to a vapor. Okay, and so what we find in this case is that the temperature at my azeotrope is greater than either pure component. Right, it's actually harder to boil that mixture than it is either pure component. Okay. The last 2 things I'll point out, or last thing I'll point out, is the line on the bottom is my bubble line, right, separating liquid from 2-phase. The line on top is my dew line, separating vapor from 2-phase. If I start to the left of my azeotrope, heat myself up into the 2-phase region, okay, I get phase splitting along an isotherm. What you'll notice is here, your bubble line is to the right. So to the left of my azeotrope, I actually concentrate component 1 in the liquid and not in the vapor. And when I'm to the left or to the right of my azeotrope, I heat myself up into the 2-phase region. I get phase splitting along an isotherm. Now my vapor phase is more rich with respect to the most volatile component, or Y1's greater than Z1 or greater than X1. Okay, so on both sides of the azeotrope, you get opposite behavior in terms of who's behaving in this most volatile component, and this is opposite as what we just saw for a minimum boiling azeotrope. Okay, maximum boiling azeotrope, right? You will not get a flat region in your bubble line. Right, the components really like each other, so they'll form miscible liquids. And then what's plotted here is a PXY. Just as the last example, PXY things essentially just flip. Here we identify volatility based on saturation pressure, and we find that the saturation pressure of this azeotropic mixture is less than either pure component. Okay, cool. All right, and if you really like azeotropes, all right, again, these put limits on your achievable separation, and so specialized distillation processes are required, or specialized separation processes, if you desire to get a mixture more pure than that azeotropic composition. but that's a discussion well beyond it. But even if you start to think about what's happening at a molecular level in both cases, one of these strategies to break azeotropes is called, extractive distillation, where I would add a third component to try and improve, essentially the volatility of that most volatile component, or to, decrease the volatility of the least volatile component. And if you think of these things, in terms of what's going on at a molecular level, you could already begin to think about these processes and how you might design them. Okay, and that is the end of our notes on azeotropes.